We will continue on the urinary system. First, we'll see the three processes of urine formation. You know that inside the kidney you have nephrons, and nephrons are the functional units of the kidney. And you also know that the nephron has different parts. We talked about that in last class, different parts of the nephron. And inside the nephron, the urine formation takes place. So formation of urine is the function of a nephron. Three processes of urine formation are filtration, which is also called glomerular filtration. Another process is called reabsorption. And the third process, that is called secretion. So these are three processes of urine formation. Glomerular filtration occurs here. You know, afferent arteriole, then the ball of capillary here, that is called the glomerulus. We have talked about that in last class, a ball of capillary that is called the glomerulus, this one. And this is called the Bowman's capsule. Also called glomerular capsule, that covers the glomerulus. So this is glomerulus, you see the ball of capillary or tuft of capillary, and this is the Bowman's capsule that is like a cup that covers the glomerulus. So Bowman's capsule is therefore also called glomerular capsule around the glomerulus. Now, what is glomerular filtration? You know that blood circulates inside the glomerulus, right? Blood flows for a long time. You remember in last class I mentioned why? Because in that tuft or ball, capillary is very long, right? So blood stays there, circulates there, flows there for a long time. And that when the blood circulates through the glomerulus, through the wall of glomerular capillary, fluid comes out. Remember, the wall of glomerulus is very porous. I mentioned that in last class too. The capillary wall here is very porous, lot of pores, right? So the fluid can easily get out from the blood through the capillary wall, and then the fluid also passes through the Bowman's capsule and enters here, and this process is called filtration. The fluid from the blood enters into the nephron, and now you know that to move the fluid from one place to another, you need what? What do you need? Pressure, right? Without pressure, the fluid will not get out. Is it clear? So, now you tell me, to move the fluid from the blood here in the glomerulus to the nephron here, the pressure must be higher where? Here, right? So that will push the fluid from the blood to here. Is it clear? So the pressure of fluid here is higher than here. And how much higher? Normally about 10 millimeter of mercury. So that pressure is 10 millimeter of mercury. That pushes the fluid out from the blood. So that is the filtration. Then after the filtration, this fluid starts to pass through the nephron, different parts of the nephron, and finally gets out as urine. So urine is the fluid that gets out from this last part of the nephron. Okay? While the fluid passes through the nephron, that tubule, what happens? Reabsorption and secretion. Now what is reabsorption? Very simple. Getting out from the tubule through the wall of the tubule or nephron. That is called reabsorption. Now remember the term reabsorption. Why we say reabsorption? When you just think, when you drink water, okay? First absorption takes place where? In your intestine, you know that, right? Water is taken into the blood, right? Now after filtration, again it is getting back into the body through the wall. That's what is called reabsorption. Second time it is happening. Is it clear? That's why we use the word reabsorption. Anyway, so remember when reabsorption occurs, that gets back into the body. Inside from the nephron gets back into the body. That is very important. Anything reabsorbed, that means getting back into the body, will remain in your body. Secretion is just opposite of reabsorption. Secretion is from the body tissue through the wall of the nephron. It is getting in to the nephron. So secretion is just opposite of reabsorption. So reabsorption takes the chemical back into the body from the nephron. Secretion is opposite. From the body through the nephron wall of the nephron gets into the tubule or nephron. Secretion of anything will let it get out through the urine, because you see here, if secretion occurs, that means from the body tissue that chemical is getting in to the nephron and eventually get out as or with the urine. Reabsorption means it is not letting get out through the urine, taking it back before the urine gets out from the nephron. So those are the three processes of urine formation. All these three must occur, and finally the fluid will remain here, will get out as urine. Okay?
So it's filtration, reabsorption, and secretion.
Right, those are three processes. Okay? Now you tell me, simple question, if I ask you, if reabsorption of water occurs more in your kidney, nephron, reabsorption of water occurs more, the volume of blood will go up or down. Reabsorption of water, that means water is getting back where? To the body, right? That will increase the blood volume. Make sense? If secretion of chemical occurs more, that means in your body it is going down. Is it clear? Because secretion is opposite. So those are three processes. You all know that if hydrogen ion concentration in your blood increases, that means the pH goes down, right? Remember that? More hydrogen means pH what? Less. Acidic, right? Body will become acidic. Make sense? Which is not good. Acidosis will occur, right? More hydrogen. In that case, you tell me what the nephron should do. Let secretion occurs more, or reabsorption of hydrogen ion should occur more. First thing simple. In your blood, you have more hydrogen ion, right? Acidosis. So your kidney should preserve hydrogen ion or let it get out. Is it clear? So which one should occur, reabsorption or secretion? Secretion, right? Because secretion will give it from the body to the nephron and will get out from the body. Is it clear? So you need to think why we need reabsorption, why we need secretion. It is not fixed. The volume or amount is not fixed, right? If in your body something is more needed to be excreted, secretion should occur more, right? If your body needs to preserve it, retain it, hold it, reabsorption should occur more. Is it clear? Okay. So these are the three processes. Now, the filtration pressure is 10 millimeter of mercury. This 10 millimeter of mercury is the net result of three pressures. Three pressures are present here. This is the final pressure that pushes the fluid out, 10 millimeter of mercury. So, what are the three pressures in this area we have? Those three pressures are glomerular hydrostatic pressure, which is the pressure in the glomerulus, pressure of fluid in the glomerulus, that means in the blood. And this pressure, glomerular hydrostatic pressure, is trying to push the fluid out this way, working this way. Glomerular hydrostatic pressure in the glomerulus. And there are two other pressures, they are trying to stop that. That means those are opposing pressures. What are those? Colloidal osmotic pressure in the blood. You remember when we talked about the blood, do you remember the term colloidal osmotic pressure? Albumin, three plasma proteins, remember that? Albumin, globulin, fibrinogen. Albumin is responsible for colloidal osmotic pressure. That tries to hold the water inside the blood, right? Will not let it get out. You must remember that, right? So this pressure is trying to hold the water or fluid in the blood, will not let it get out. So this is one opposing pressure. Another opposing pressure is capsular hydrostatic pressure inside the Bowman's capsule. So now one pressure is trying to push the fluid out to cause the filtration. Two pressures are trying to stop that. Is it clear? Now, that first pressure that is trying to push the fluid out must be more than the combined pressure of those two, right? To cause the filtration. So I think that this way. You are pushing something, okay, in one direction, and your two kids are trying to stop that. Make sense? And your pressure is like 50 pound, and your two kids together is 40 pound. Make sense? Then, although the number is more in your other side, but which way the thing will move? The way you are pushing, right? Because your pressure is more than their combined pressure. Is it clear? So, the difference is 10 millimeter of mercury. Here, you see in this picture, the glomerular hydrostatic pressure that is favoring the filtration is 55 millimeter of mercury, and colloidal osmotic pressure is 30 millimeter of mercury, and capsular hydrostatic pressure is 15 millimeter of mercury. Now, those two, they are trying to stop together is 45, 30 plus 15, 45 millimeter of mercury, and favoring pressure is 55. So 55 minus 45 is 10 millimeter of mercury. That's the net filtration pressure. That causes the filtration. Now you tell me, if the colloidal osmotic pressure becomes 40 here, just do the math. If the colloidal osmotic pressure becomes 40, then what will happen? Because same. Make sense? So no movement. Is it clear? So to cause the filtration, to produce the urine, filtration must occur, right? Filtration must occur. Fluid must enter into the nephron, otherwise urine formation will not occur. So these pressures are very important. Make sense? Okay. Glomerular filtration rate is the volume of fluid formed in each minute by both kidneys together. So your two kidneys have more than 2 million nephrons, and all those together are forming how much fluid in 1 minute. That is the glomerular filtration rate. And your two kidneys, that means all the nephrons inside the kidneys, if they are functional, in 1 minute causes 120 to 125 milliliter of filtered. That means this, how much volume is entering here by filtration with all the nephrons together in both kidneys. That is 120 to 125 milliliter per minute. Now, three factors can directly change the amount of filtration or filtration rate. What are those three factors? One is total surface area for filtration, another is permeability of filtration membrane, and net filtration pressure, which is 10 millimeter normally, but if that pressure changes, I have mentioned already, the volume will be more or less. So now, what is total surface area of filtration? Think here, this is the glomerulus. Now, very simple way, if you want to think, if I make this glomerulus straight, that capillary straight, and measure the total surface area, if this is the surface area of this glomerulus and another glomerulus is smaller, so this is another glomerulus which is smaller. Now if I make it straight and measure the surface area, in this case total surface area will be less, right? Is it clear? Because this is shorter if you make it straight. So now we know that in the wall of your capillary, glomerular capillary, you have pores, many holes. We already know that, right? Very porous. So this one got more holes because the surface area is bigger. This one, total surface area is less, so less pores. So in this case, filtration will be more, the fluid will get out more. In this case, it will be less. Is it clear? So that is the total surface area available for filtration. Permeability of filtration membrane. Now think that both are the surface area in both is same, but in this case this person got disease, for example infection, chronic infection. So although the size of glomerulus is same in both cases, since this person got infection, chronic infection, many of these pores got closed. Some are open or some are partially open. Make sense? That can happen. The quality of the capillary wall can be changed, and in that case filtration will occur more through the healthy one, less through this one. So not only the size of the surface area is a matter, the quality or the permeability of the membrane is also important. Net filtration pressure that I have already mentioned is 10 millimeter of mercury that pushes the fluid from here to here, but if that amount changes, the volume of filtration will be different. So more pressure difference, more filtration. Less pressure difference, less filtration. So those are the three factors that can directly influence the glomerular filtration. Okay, now we'll come back here. After filtration, the fluid is here. Then what happens? This fluid starts to pass through the nephron. Starts to pass through the or move through the nephron. When the fluid passes through this part, this is called the proximal convoluted tubule. This part of tubule is convoluted like this, and this is called proximal convoluted tubule. This is called distal convoluted tubule. Okay. So when the fluid is passing through the proximal convoluted tubule, water and other solids will be reabsorbed. How much? 65%. That means a lot. 65% of water and other solutes will be taken back into the body, reabsorbed. How much? 65%. Now you tell me, if this is hypothetical, if the volume of filtration here is 100 microliter, look at this picture. So filtration amount is 100 microliter here, and when this fluid is passing through the proximal convoluted tubule, 65% of it is taken out from the nephron. Then when the fluid will arrive here at the end of proximal convoluted tubule here, what will be the volume? Very simple question. You have $100, okay? If I take $65 from you, how much you have left? How much you have left? 35, right? Is it a difficult question? So same thing, 100 milliliter or microliter was there, right? And when it passes through the proximal convoluted tubule, 65% is taken back. Is it clear? So how much volume of fluid will be here when it will arrive here? 35 microliter. Make sense? This volume is just hypothetical. So that's how much volume will arrive here. Now, another thing, that is one thing. Number two is I mentioned that water and other solutes will be reabsorbed. Now, you think you have a solution of glucose, sugar. You have mixed sugar and water, okay? You got the solution of sugar. Is it clear? Now, this is very important to understand kidney function. Very simple but very useful. Now, you have that solution, that fluid here. Now, if I take the sugar part out only, the concentration of that solution will increase or decrease? Decrease, right? It will get more dilute because I am taking the solute out. Is it clear? Now, if I take only water part out from that solution, I take only the water out, what will be the change? Concentration will increase. Clear? Very simple, like you have solution here in the container, glucose solution. That means you have water and what? Glucose. Water is solvent, glucose is what? Solute. Now if I take only glucose out from here, the concentration will go down. If I take only the water out from here but let the glucose stay there, right? The volume will be less, right? Because I am taking the water out, but concentration will be high. Is it clear? You have to understand this to understand the kidney function, okay? And this is very simple. Now you tell me, if I check water as well as glucose, both out from that solution equally, the volume will be what? First tell me the volume. I am taking water and glucose both out. Volume will get smaller, right? Concentration will remain same because I am taking out both proportionately equal. Okay, so the volume will go down, but concentration will remain same. Understand this? Okay. Now, in proximal convoluted tubule, 65% of everything, water as well as the other solids, will proportionately get out. That means the volume will be reduced significantly, 65%, but the concentration will remain same here and here because everything is getting out proportionately. Is it clear? Okay. So in proximal convoluted tubule, volume decreases a lot, right? But the concentration remains same. Okay. Now the fluid will pass through the loop of Henle, this hairpin-like or loop-like structure. This loop of Henle has two parts. You see, the descending limb and ascending limb. So when the fluid will pass through the descending limb of loop of Henle, see what happens here. Only water will get out, reabsorbed. So reabsorption of only water. will occur here. Now you tell me the fluid is going down this way through the descending limb of loop of Henle. Fluid is going down and the water only is getting out from here, from this fluid. Water is only getting out. So the concentration of fluid will be what? Here. Water is getting out. Higher, right? So as the fluid goes down through the descending limb, the concentration of fluid increases. Is it clear? But the volume decreases because water is leaving, right? So the concentration increases a lot, but the volume decreases. The concentration of fluid here in the proximal convoluted tubule is about 100 to 300 milliosmol. That is the unit of concentration. 100 to 300 milliosmol in this part. And when the fluid, you see here, arrives here at the bottom of the loop of Henle in long loop nephron, the concentration increases a lot because a lot of water gets out and it becomes 1200 to 1400 milliosmol. So significant increase of concentration at the bottom of the loop of Henle. Is it clear? Okay, now this fluid from here will move up through the ascending limb of loop of Henle. And when the fluid will move through the ascending limb of loop of Henle, what will happen? If this part, no water reabsorption will occur, but sodium chloride and some potassium will leave the fluid. So water is remaining here, but the solutes are getting out. Is it clear? Which solutes? Sodium, chloride, potassium. You know, sodium chloride is salt, right? Sodium, chloride, potassium. So now you tell me, very simple question. If from this fluid only the solutes leave, water remains there, you are taking the solute out, like glucose out from here, water is staying there. Then as the fluid is moving up, the concentration will increase or decrease? Concentration. You are taking the solutes out, water is remaining there. Decrease, right? Is it clear? So as the fluid moves up through the ascending limb, since the solutes, sodium, chloride, potassium, get out, reabsorb, the concentration goes down. And here, when the fluid arrives at the end of the loop of Henle, the concentration is now close to this, 100 to 300 milliosmol. That comes back again here, because you see the level is same. Okay, so that is what happens when the fluid is passing through the loop of Henle. Okay, is it clear? So if I ask you, the wall of descending limb of loop of Henle is only permeable to what? Water, right? Only water can pass through it. Is it clear? No other no solids. When the fluid passes through the ascending limb, only these solutes can pass through it. Okay, now the part here, this is the distal convoluted tubule. Distal convoluted tubule. And this part is interesting. Why? Because hormone works on this part, very important hormone, that is called aldosterone. Aldosterone is the hormone that works on the distal convoluted tubule on this part. This aldosterone comes from the adrenal gland. You remember on the top of the kidneys you have adrenal glands. You have learned that in NP1, suprarenal or adrenal glands. So when the fluid is passing through the distal convoluted tubule, and aldosterone does what? Aldosterone helps in the reabsorption of sodium. So in this part, sodium reabsorption occurs with the help of what? The hormone. Which hormone? Aldosterone. Comes from which gland? Adrenal gland, right? On the kidney, you know, adrenal gland on the kidney. Second? Sodium. So aldosterone helps in sodium reabsorption in which part of the nephron? Distal convoluted tubule. Is it clear? More aldosterone means what? More reabsorption of sodium. Now, when sodium moves, remember, in this part, sodium takes the water with it. Sodium has a tendency to hold the water molecule. So when sodium reabsorption occurs in this part, the sodium takes water with it. So also water leaves the nephron in this part. Now, in exchange of sodium, when one sodium leaves, gets out, one potassium ion is secreted. That means get in. So sodium gets out, in exchange the potassium gets in. That exchange mechanism takes place here. Sodium is reabsorbed, potassium is secreted. So now if the aldosterone is secreted more sodium is reabsorbed here in this part. This is very important. More sodium is reabsorbed, taken back into the body, and sodium takes water with it. So more water is reabsorbed. Is it clear? So more water gets back into the body. If more sodium and water gets back into the body, enters into the body, the blood volume increases, right? That I mentioned before. Water is getting back into the body. Blood volume will go up. So blood pressure will go up. Is it clear? So the aldosterone increases the blood pressure. Make sense? By increasing the volume. Working where? On the nephron. On which part of the nephron? Distal convoluted tubule. Make sense? So you have millions of nephrons, right? So aldosterone is working on those. So a lot of reabsorption of water is being taken place. So this is a very important hormone that increases the blood pressure. Now the fluid enters here in the collecting duct. Last part, collecting duct. And when the fluid passes through the collecting duct going this way, this part is very sensitive to another hormone. That hormone is called, all of you have heard that hormone is called Antidiuretic Hormone or ADH. Have you heard this? ADH, antidiuretic hormone. This hormone works particularly on the collecting duct, this part. This hormone comes from the posterior pituitary gland, posterior pituitary. It is a posterior pituitary hormone. Its name is telling you its function, right? Antidiuretic. Have you heard the word diuretics? Diuretics? Diuretics do what? Produce more or less urine? More urine, right? So antidiuretic will do what? Less urine, right? Anti. We all know diuretics like coffee or alcohol, right? Produce more urine. Have you heard that? We say natural diuretics. Some medicines can produce more urine, right? You know that? If someone's blood pressure goes up, you cannot control, then the doctor will give the medicine that will produce more urine. Have you seen that? More urine and like Lasix, and that will decrease the blood pressure. So that is diuretic, right? Medicine. Some food could be diuretics. Anyway, so antidiuretic hormone does what? It reduces the volume of urine, decreases the urine production. Is it clear? So what should happen here? When the fluid is passing here through the collecting duct, and when antidiuretic hormone works on this, to reduce the volume of urine, here, water should be reabsorbed. Is it clear? Water should go back into the body from the nephron. So antidiuretic hormone or ADH causes reabsorption of water. Water is taken back or out, taken back from the into the body, taken out from the collecting duct. So more ADH means less volume of urine, right? Now you tell me, if I stop the secretion of ADH from the pituitary, no ADH will work here. Is it clear? No production of ADH, no secretion. So what will happen? No reabsorption of water will occur here. Water will remain here, right? So the volume of urine will go up. Is it clear? Volume of urine will go up. But your body is losing what? Water. More urine means your body is becoming dehydrated. Is it clear? Because water is not going back. You are producing more urine. So eventually you will get dehydrated. So ADH is very important hormone. Comes from which gland? Posterior pituitary, right? Works on which part of the nephron? Collecting that, right? And doing what? Reabsorption of water. Is it clear? And reduces the volume of urine, urinary output. So now you see the entire nephron. Look at this. The entire nephron, I can divide it into two parts. The first part or early part, if I divide here, this part is not sensitive to any hormone. Is it clear? No hormone is working here, right? And this part is sensitive to hormones. Is it clear? Which two hormones are working? In this part, aldosterone, in this part, ADH. So this is hormone sensitive part, right? This part is what? Non-sensitive. That means which part is fixed? Which part can be changed? This part is fixed, right? This part depends on the hormone, right? If hormone is secreted less, change will be less, right? More, less. So now if I ask you, in which part the concentration and volume of urine is regulated, in this part, right? Because this part is fixed. It will happen more or less same amount. Okay, no hormone, no regulation. But regulation of volume and concentration is controlled in this part, hormone sensitive part, the last part of the nephron. Make sense? Okay. So if your kidneys want to produce less urine, the secretion of ADH should be more. More urine, ADH secretion should be less. Okay. Blood pressure is also will be controlled by this part, by changing the volume. Okay. I believe I mentioned this in last class. Juxtaglomerular apparatus, granular cells secrete a chemical that is called renin. And that renin is important to regulate the blood pressure. Why? Because renin works on a protein that is called angiotensinogen, and that angiotensinogen is an inactive protein in the plasma of your blood. And renin converts the angiotensinogen to angiotensin 1, and angiotensin 1 is then converted to angiotensin 2. The most active form is angiotensin 2 by an enzyme that is called ACE. Very simple, angiotensin converting enzyme, ACE. So that converts the angiotensin 1 to angiotensin 2. Angiotensin 2 is the most active chemical or protein that works on a number of areas. The most important is angiotensin 2 works on the blood vessels of your body and causes generalized vasoconstriction. That means generalized means not localized. Generalized means everywhere. Is it clear? So, on all the blood vessels, angiotensin 2 will cause what? Constriction. And if you constrict the blood vessels, the pressure goes up, right? If the blood vessels get narrow, you know that increases the blood pressure. So angio, its name is telling you, angio indicates the blood vessels, tensing, pressure, okay? It causes pressure increase by generalized vasoconstriction. That is the most powerful action, but angiotensin 2 has other actions too. Now, you see the effect of angiotensin 2. One I have already mentioned, constrict the blood vessels, generalized vasoconstriction, working on the smooth muscle in the wall of the blood vessels, and that increases the mean arterial pressure. Very simple. Stimulates the reabsorption of sodium in the nephron. You must remember, I mentioned, when sodium reabsorption occurs, sodium takes the water with it. So that action is on the nephron, tubule. Renal tubule is the nephron. And more sodium reabsorption means more water reabsorption, means higher volume of blood in the body, and that increases the blood pressure too. Also, angiotensin 2 stimulates the adrenal gland to secrete more what? Aldosterone. Remember, the aldosterone works on this part of distal convoluted tubule. I mentioned the adrenal gland sitting on the kidney, right? So more aldosterone is produced. That means further sodium reabsorption occurs. More water gets back into the body. Blood volume increases the blood pressure. So directly causes sodium reabsorption, angiotensin II. Also stimulates the adrenal gland to release aldosterone that causes the reabsorption, further reabsorption of sodium. Is it clear? So directly and through the aldosterone. Stimulates the hypothalamus to release the antidiuretic hormone. Now you all know antidiuretic hormone is secreted by posterior pituitary, right? You remember a few minutes ago I mentioned. Then why hypothalamus? You also know, if you remember LP1, hypothalamus, and this is the pituitary gland. So hypothalamus is sitting just above the pituitary gland and regulating the secretion from the pituitary gland. Hypothalamus is here, and that sends signal to the pituitary to release ADH. All pituitary secretion is controlled by hypothalamus. So, master of the master. Pituitary is the master gland, but it has also a boss, hypothalamus. So, if hypothalamus is stimulated by angiotensin II more, it will send signal to posterior pituitary more to release more ADH. Is it clear? ADH will go to the kidney, work on the last part of the nephron, collecting that, reabsorb more water, blood volume will increase, the blood pressure will increase. Is it clear? So you see, all these actions, generalized vasoconstriction, reabsorption of sodium directly or via aldosterone, and secretion of antidiuretic hormone, right? All these are to do what? Increase the blood pressure. Okay? By constricting the blood vessel, blood pressure increases. By increasing the blood volume, by sodium and water reabsorption, blood volume increases. So both will increase the blood pressure. So the action is increasing the blood pressure in different ways. Okay. Counter current mechanism of urine formation. This is very interesting. Counter current mechanism is a very efficient process that occurs in the nephron. You know, again I am drawing the same picture. Okay, so this is the nephron, you already know, and this is the glomerulus, all these you know, afferent arterial, efferent arterial, okay, and that efferent arterial goes like this. Along the loop of Henle. So this is the loop of Henle, that means the nephron, and this is the blood vessel. This efferent arterial forms the capillary. So from here it becomes a capillary that is called Vasa Recta. Vasa Recta. And actually the Vasa Recta, if you see, it is like a ladder, you know, the ladder to climb up like this, because two limbs of this Vasa Recta are connected by the blood vessels like this. So anyway, so this is the loop of Henle, which is a part of the nephron, and this is the capillary, loop of capillary, that is called Vasa Recta. Now, what happens here? You already know that when the fluid passes through the descending limb of loop of Henle, in this part, reabsorption of what occurs? In this part? Water, very good. Only water, right? Okay, so water gets out. Make sense? Now you tell me, you also should remember this part. When the fluid is passing through the ascending limb, who is getting out? Very good. Sodium, chloride, right? Chloride and some potassium. Remember that? Okay. Reabsorption of water in this part, reabsorption of sodium chloride, potassium in this part. Now you see, if reabsorption occurs here, water gets out, water will start to build up here, accumulate here, right? Because water is continuously getting out, right? So this is the Vasa Recta, but the blood, what the Vasa Recta is doing here is very important. This is very important. While the blood is passing this way, water is getting in from the interstitial space here. So continuously water is getting out from the descending limb of loop of Henle, but water is not staying there. Water is entering into the blood here, and the blood is taking it out. Is it clear? So water is getting out from the descending limb, reabsorption, right? But cannot accumulate there. Why? Because the blood is taking it inside. The Vasa Recta is continuously taking it in. Make sense? Otherwise, what will happen? Just think that if Vasa Recta is not here, water will continuously get out, right? At one point, what will happen? The pressure of water will be high here. Make sense? And that will stop further reabsorption of water. Because if the pressure is high here, no water will be able to get out. Is it clear? So it is continuously taking that water and taking it away. So this is very important. Otherwise, urine formation will not occur. Make sense? Okay. Now let's see this part. In this part, sodium chloride and potassium are reabsorbed, right? And these solutes are also entering into the blood here. So the concentration of sodium chloride potassium will not increase in this part. So new sodium chloride potassium can get out. So continuously the blood is flowing and taking sodium chloride potassium out from there. Yes, finally all solids are, right, going into the Vasa Recta, into the blood, right? And blood is washing them out or away. Otherwise, the concentration will increase, right? And pressure will build up. No reabsorption will occur. So you see that Vasa Recta is playing a very important role, right? And must run along with the loop of Henle, side by side, right? Otherwise, it will not be able to work. And that's why this process is very important, essential for urine formation. Now, you tell me, when the fluid is, you already know, fluid is going down through the descending limb, the concentration increases or decreases? Increases, right? A lot. Remember here, like 1200 to 1400. So concentration increases. Now you tell me here, when the blood is going down, water is getting in, right? If you add water to something, the concentration will go down, right? So as the fluid is moving down through the descending limb, concentration is going up, but as the the blood is going down through the Vasa Recta, concentration is going down. Opposite, right? Same thing here. As the fluid is going up, the concentration is going down because sodium, chloride, potassium are leaving. As the blood is going up, concentration is increasing because sodium, chloride, potassium is getting in, right, being added. So opposite, right? Here and here opposite, here and here opposite. Is it clear? Concentration. Now you tell me, it's interesting. Here, water is getting out. The volume here is getting down, right? The volume, because water is getting out. Is it clear? Here, water is being added to the blood. So the volume is going up. So you see, also volume is going in the opposite direction, right? Volume is going down in the loop of Henle, but increasing. Same thing here. Okay. So that's why it is called counter current mechanism in the loop of Henle and the Vasa Recta. The change is in opposite direction, counter. If you see inside the kidney, the nephron is actually located in this way. You remember the kidney has outer cortex, inner medulla. So this is the cortex part, and this is the deep medulla. Okay, so all the nephrons are this way. Another nephron here, another nephron here. Okay, so in the cortex part, you have these parts of the nephron. In the medulla, you have the loop of Henle. In deep medulla, you have this part. So you already know, if I take a drop of fluid from here, the concentration is very low, like I mentioned 100, could be 100 to 300. So as low as 100 milliosmol. And in the deep medulla, you have the lower end of the loop of Henle. Here the concentration could reach up to 1400 milliosmol. I mentioned 1200 to 1400 milliosmol. So now if I take a drop of fluid from here in the deep medulla, the concentration of fluid is very high. If I take from here, the concentration is very low. You see there. They have shown it. Okay? Make sense? As you go deeper, the loop is going down. Okay? Inside the kidney. I've talked about this, so you already know. This is the Vasa Recta. Urinary bladder. Urinary bladder is a hollow organ located in the pelvic cavity, and the function is holding or storing the urine for few to several hours. In the wall of the bladder, you have three layers. Innermost epithelial lining is transitional epithelium. Transitional epithelium has two very important properties I mentioned in NP1. One is transitional epithelial cells can change the shape. That's why called transitional. Change what? The shape. Can get expanded, get flat, and can get narrow like this. So by changing the shape, this epithelium can get expanded, make sense? Easily, and absorb the pressure. Absorb the pressure. So you know your urinary bladder, when it is full, right, gets bigger. When it is empty, smaller, right? And that can occur because of transitional epithelial lining there. That is one function of transitional. By changing its shape, the transitional epithelium can absorb pressure. Number two, that is very important, transitional epithelial lining does not allow any fluid pass through it. Now, urinary bladder, what's the function of bladder? Holding urine, right? So when urine is staying there for few to several hours, should the urine get back into the body or stay there? Stay there, right? If the urine gets back into the body, no point of holding there. So the transitional epithelial lining does not allow any fluid to pass through it. So if this is the urinary bladder, this is the wall, transitional epithelial lining is here, will not let the urine get back into the body. So it can stay there for hours as it is. And when needed, we just empty the bladder. The middle layer is a thick muscular layer, and this muscle is a special type of smooth muscle, and this muscle is called the tracer muscle. So middle thick layer is the smooth muscle layer, and that smooth muscle is called the detrusor muscle. This muscle has elasticity, more elasticity, can expand. And outermost layer is the fibrous adventitia. Adventitia is the outermost layer. So those are the three layers in the urinary bladder, the wall of the urinary bladder. If you cut the bladder and see inside, you will see a funnel-shaped area that is called the trigon. So if this is the urinary bladder, this is the urinary bladder, and this is the urethra. Okay, so urethra, and this part is a funnel-shaped area here above the urethra, urethral opening. This is the opening for the urethra. Urine gets out this way. So this part is called the trigon. Okay. The trigon is a funnel-shaped area like this. You see here, and urethra is here. So the urine can easily be poured into the urethral opening. You know, what's the function of a funnel? We use the funnel, right, to pour something into a narrow space or area. So the pointed lower end of this funnel or trigon is here, and that is the starting of the urethra. And there are three openings in the bladder. You know that two ureters come from the kidneys like this. So you have the opening for the ureters, two ureters. They bring the urine into the bladder from the kidneys. You already know that. So these are called ureteral openings. Okay, these two are ureteral openings. So urine gets in, and this opening is for urethra. This is called urethral opening. So there are three openings inside the bladder. Two for the ureters, ureteral, one is for urethra. Urine gets out. Okay. Okay. Now, the urethra is the last part of the urinary system. And this part is different in male and female. You must remember that. So the urethra is different in male and female. Male urethra is much longer than the female urethra. And if you see the length of a female urethra, it is 3 to 4 centimeters. That means short. And male urethra is 15 to 20 centimeter long. 15 to 20 centimeter. So much longer. In male urethra, there are 3 parts. The part inside the prostate is called the prostatic part or prostatic urethra. That's the first part of male urethra. Then second part is very short, only about 2 centimeter long, and this part is surrounded by a diaphragm, a muscle like this, that is called urogenital diaphragm. And third part is the longest part, about 15 centimeter long. This is inside the penis, and this part is called the spongy urethra. Now, if you see this picture, you see the part inside the prostate, that's the prostatic urethra. And now you see the middle part, you see the diaphragm, a flat muscle is going like this. And inside that diaphragm, that part is the membranous urethra. The diaphragm is called urogenital diaphragm. So in your body, in the body cavity, you have 2 diaphragms. One you already know, the big one is here, right? Diaphragm here, and another diaphragm is here. That is much smaller diaphragm, but both are flat muscle. Diaphragm is like this, urogenital diaphragm is like this. See. And this is urogenital diaphragm, and the part of urethra inside is the membranous urethra, this part only. And the last part is the spongy urethra. In male urethra, you have 3 types of epithelial lining. What are those 3 epithelial lining? Most part is pseudostratified columnar epithelium. Only the first part and the last very small part, those 2 parts are lined by 2 other types of epithelium. Now let's see here. That makes sense because you see here, this is the male urethra. This is the male urethra, long. Okay. Most part of it is pseudostratified. Pseudostratified columnar. Anybody remember pseudostratified columnar cells have what? Something interesting. Cilia, right? Remember that? That's why we say pseudostratified ciliated columnar. And most part of the urethra has pseudostratified ciliated columnar epithelium. You know that mucus is secreted here, so that should be pushed out, the slippery secretion. So that's why we have pseudostratified ciliated columnar. Make sense? Cilium bit like this to push the mucus out. Also, the fluid, if the urine stays there, right, should be pushed out. So that helps. Only the very first part is transitional. That makes sense because transitional epithelium. Urinary bladder has what kind of epithelium? two important functions I mentioned, right? Doesn't let the water pass through it and can stress, right? So what kind of epithelium urinary bladder has? Transitional, right? Remember that? So now you see that from the urinary bladder, transitional epithelium continues. That makes sense. A little bit like this and gets into the first part, very first part of the urethra. Make sense? So from the bladder, it goes into the very first part of the urethra like this, and it stops there. So that's why the first part is transitional, because urinary bladder is transitional and that continues a little bit here. Now the last part, this last part of urethra is getting exposed to the outside of the body, air, outside of the body. So this last part should be what kind of lining? What do you think? The chance of friction is high, right? Because that's the very last part, end part, and getting exposed to the air. Your skin is exposed to the air, right? What kind of epithelium? Stratified squamous, right? Because I mentioned many times, friction in the mouth, right? Esophagus, where the chance of friction is high, stratified squamous. So that's why, and all this makes sense, right? Pseudostratified ciliated to push the fluid, right? And keep the urethra empty and clean. And first part, since urinary bladder is transitional, that continues a little bit into the urethra. And last part exposed to the air, right? So outside is stratified squamous. Sphincters. In the urethra, there are two sphincters. One is here, internal urethral sphincter, another is here, that's the external urethral sphincter. Now, like the anal canal, you remember internal and external anal sphincters? Similar, very similar. This is internal sphincter, this is external sphincter. External is skeletal, that means voluntary or involuntary? Voluntary. And inner is smooth, that means what? Involuntary. Both remain closed in normal condition. When we decide to urinate, we voluntarily relax the external urethral sphincter. So this one gets open. When we do that, relax this muscle, signal goes to the spinal cord. And the spinal cord sends a signal to the inner one, internal sphincter, because you cannot control this. So your central nervous system sends signal and opens this one. So when both are open, urine gets out of the body. Make sense? Then you use the pressure, of course, using muscles that creates pressure on the bladder, but those sphincters must be open, right? Otherwise urine will not be able to get out even if you press on the bladder. So that's how urination takes place. Should I stop here? Okay, couple more things. I will talk about that in next class, that's fine. Okay.